Hello, I'm Dr. Maurice Dupre, and in this section we're going to discuss indeterminate forms and L'Hopital's rule. Now, you can remember from the definition of the derivative that when you go to calculate the limit, it always is a limit of the form 0 over 0. Other times when we're calculating limits, we effectively have to deal with something that looks like it's going to infinity over infinity. We call things like that indeterminate forms. Now, because the derivative, in effect, is an indeterminate form, it's actually not too surprising that the derivative can be used to actually deal with indeterminate forms. Let's see how this is done. L'Hopital's rule, the stronger form. Suppose that f of a equals g of a equals 0, that f and g are differentiable on an open interval I containing a, and that g prime of x is not equal to 0 on I if x is not equal to a. Then the limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of f prime of x divided by g prime of x, assuming that the limit on the right side exists. That is, keep in mind, if this limit exists, in particular, then this limit exists. And to compute this limit, what I do is, look, it's a quotient. I differentiate the numerator, differentiate the denominator, so I form f prime of x over g prime of x, and then I try to take the limit as x approaches a again. Notice I did not differentiate here by the quotient rule. The numerator is differentiated by itself, the denominator is differentiated by itself. So we are not applying the quotient rule here. Don't make that mistake. Now, anything that can be done once like this can be done again. For instance, if I look at this and I say, well, I can't tell whether this exists or not, and I look and see it's of the form infinity over infinity or 0 over 0, I can apply this whole process again. So this is the technique of using L'Hopital's rule to find the limit as x approaches a of f of x over g of x. To find this limit by L'Hopital's rule, continue to differentiate f and g so long as we still get the form 0 over 0 at x equal a. But as soon as one or the other of these derivatives is different from 0 at x equal a, we stop differentiating. L'Hopital's rule does not apply when either the numerator or denominator has a finite non-zero limit. That's one of the most common mistakes that students make, is they get used to applying L'Hopital's rule to indeterminate forms, and then they're dealing with suddenly a limit which is not an indeterminate form, and they try to apply L'Hopital's rule. In fact, if it's not an indeterminate form, L'Hopital's rule is virtually guaranteed to give you the wrong answer, so don't make that mistake. Well, now to begin, let's calculate some limits using L'Hopital's rule and using our old methods to see how they compare. Here in this problem, I have the limit as x approaches infinity of 5x squared minus 3x, all divided by the quantity 7x squared plus 1. So notice, if I look at the numerator by itself, as x goes to infinity, the result would be infinite, because the x squared will certainly overpower the x. For instance, if x is a billion, then x squared is going to be way bigger than simply a billion. Now, the same thing is true for the denominator. Both the numerator and the denominator are becoming infinite as x approaches infinity. And so we say this is an indeterminate form, of the form infinity over infinity. And so that means it's a candidate for L'Hopital's rule. To apply L'Hopital's rule, we simply differentiate the numerator. Well, what's the derivative? 5x squared, the derivative is 10x, minus the derivative of 3x, that's just 3. So there's the derivative of our numerator. And what about the denominator? The derivative of 7x squared is 14x. The derivative of 1 is 0. Notice I have differentiated the denominator by itself, the numerator by itself. I did not differentiate the whole expression using the quotient rule. And so what we want to do now is look again at the limit as x approaches infinity of that expression which resulted. Notice as x becomes infinite, the numerator still becomes infinite and the denominator still becomes infinite. And so we still have this indeterminate form, infinity over infinity. And so L'Hopital's rule says if this limit exists, then it equals the result of what we would get by differentiating the numerator and denominator again separately. So let's do it again. The derivative of the numerator is simply 10. The derivative of the denominator is 14. And so now the question is, does this limit exist? Well, that limit exists and is obviously 10/14. Well, canceling 2's, we're going to get 5/7. So pretty easy 2 steps here of simple differentiations. L'Hopital's rule gave us the answer. Now what about using our original methods in this case? When you see a rational function like this, what you do is look for the highest power of x and divide every term by that power of x. In this case, it's x squared. So we would have 5x squared over x squared is simply 5, minus 3x over x squared is 3 times 1 over x, divided by 7x squared over x squared is 7, plus 1 over x squared. And there we want to take the limit as x goes to infinity in this expression. Well, now as x goes to infinity, 1 over x goes to 0. This goes to 0, so all of that's wiped out, and we're just left with 5/7. This technique of dividing by the highest power is pretty quick for these rational functions. In fact, it's pretty clear that when you look at this situation, if the degree of the numerator and the degree of the denominator are the same, then you're going to get simply the coefficients of the highest power terms as a fraction. There's the answer sitting right there in this case. Be aware, though, be careful. Sometimes some sneaky person will give you a tricky problem by doing something like this. They get you used to looking at just those leading coefficients like that. And if I put in, for instance, a negative x squared right here, well, that would mean that the actual leading coefficient for the x squared term is really only a 6, and the answer would be 5/6. So don't forget to look at everything. Don't just key in on the first 2 coefficients when you see it's looking like the polynomials are written in order of descending degrees. Maybe somebody snuck in a high degree term down the line somewhere. Let's look at a problem where L'Hopital's rule will really save us some work. Here in this problem, I want to compute the limit as x approaches 0 of the quantity 1 minus cosine x divided by x squared. Notice as x goes to 0, cosine of x goes to cosine 0, which is 1, and 1 minus 1 is 0. On the other hand, obviously, as x goes to 0, x squared goes to 0, and so this is an indeterminate form. Let me just write this. Indeterminate form, 0 over 0. So L'Hopital's rule says, well, we can differentiate the numerator and differentiate the denominator and try taking the limit again. The derivative of the numerator is, well, derivative of 1 is 0. Derivative of cosine x is negative sign, so the derivative of negative cosine x is positive sign. So the numerator becomes, after differentiation, sine of x. Derivative of x squared here is simply 2x. And so now I want to take the limit as x approaches 0 of sine x over 2x. Notice that, again, is an indeterminate form, 0 over 0, because as x goes to 0, sine of x goes to sine 0, which is 0, and of course the denominator 2x goes to 0 as x goes to 0. Of course, we all recognize this simple limit. We just take the 1/2 out. It's 1/2 times the limit as x goes to 0 of sine x over x, which is, of course, the standard limit that we know. Limit as x approaches 0 of sine x over x is 1, and so we would just get a half. But let's use L'Hopital's rule again. What's the derivative of sine x? Well, the derivative of sine x is cosine x. What's the derivative of 2x? That's 2. So now we want to take the limit as x approaches 0 of cosine x over 2. Well, that's now simply cosine 0 over 2, which is 1/2. Why couldn't I use L'Hopital's rule again? Well, notice this is no longer an indeterminate form. The denominator is non-zero, and it obviously has non-zero limit too. In fact, it's just a constant. So that rules out using L'Hopital's rule again, I know, to stop differentiating. All right, well, we just saw how easy the limit is to compute using L'Hopital's rule when it's in the form 0 over 0. Let's try this same problem again, but without using L'Hopital's rule. So remember, our problem is to compute the limit as x approaches 0 of the quantity 1 minus cosine x, all divided by x squared. Well, again, this is indeterminate of the form 0 over 0, but now what we're faced with is the problem of making some kind of algebraic rearrangement on this thing so that the limit will make sense. What can we do? One thing we might try, and this would probably be your first attempt, is to say, well, this is the limit as x approaches 0 of, and you would remember, well, the limit is of 1 minus cosine x over x. That one you know. What's that? That's 0. So that would be 1 minus cosine x over x times 1 over x. But again, here we still have something that in reality is indeterminate. This is 0, and this is 1 over 0, you see, and so we've got a problem. So that's not going to work for us. One thing we can do here is a kind of a trick, and there's probably a good chance that most students would not remember to do this or think to do this, but the thing that's causing the problem is this difference of two terms going to the same value 1. And so consequently, let's just multiply by the sum of those two terms and divide by that. Notice as x goes to 0, down here, this is going to 1 plus 1, which is 2. So we have not introduced any further problem in the denominator by doing this. But on the other hand, when I multiply these two terms together, notice I get 1 minus cosine square. What's 1 minus cosine square? That's sine square. So what we get here is sine square x divided by x squared times the 1 plus cosine x. So this is what we want to take the limit of. In other words, let's come down here. We want to take the limit as x approaches 0 of sine square x over x squared times 1 plus cosine x. At this point, we can say, well, we know the limit of sine x over x as x approaches 0 is 1. So this would be the limit as x approaches 0 of sine x over x, quantity squared, times the limit, let me come down here, the limit as x approaches 0 of 1 over 1 plus cosine x. In other words, this factor multiplied by this. Well, this factor is just 1 squared, which is 1, and here we have 1 over 1 plus cosine 0 is 1/2. And so we end up finally with a half, but notice how hard we had to work for it. We had to introduce these extra factors here, trig identities, all kinds of things, whereas using L'Hopital rule, all I had to do was just differentiate a few times. All right, let's calculate another limit using L'Hopital's rule. Here, let's calculate the limit as t approaches 0 of sine t squared divided by t. Notice we're getting 0 in the denominator and sine 0 in the numerator, and sine 0 is 0, so this is indeterminate of the form 0 over 0. And so consequently, we can use L'Hopital's rule. This will be the limit as t approaches 0 of the result of differentiating the numerator and the denominator separately. The derivative of the numerator, in effect, is differentiated by the chain rule. Notice there's an implied parenthesis there in our standard notation. So the outer function being sine, its derivative is cosine of t squared multiplied by the derivative of what's inside, 2t, and that's all divided by the derivative of t, which is simply 1. Now we no longer have an indeterminate form. We have something in the numerator, but in the denominator we just have a constant 1, which is different from 0. And so now we just plug in t equals 0 to get the limiting value, and obviously we get cosine 0 times 0, which is 0. And so there's our limit. One thing you could notice here is that we could have gotten this from our standard limit as x approaches 0 of sine x over x being 1. What I could do is write this as limit as t approaches 0 sine t squared. And now, since I only have a t down here, I can put a t squared there if I put a t up here. And so that would be the limit as t approaches 0 of t multiplied by the limit as t approaches 0 of sine t squared divided by t squared. As t approaches 0, t squared approaches 0, so sine t squared over t squared goes to 1, but here we have 0, so the answer is 0 times 1. Still, it's a little more work here than just using L'Hopital's rule. Okay, let's work a problem using L'Hopital's rule where we have trig functions and the point where we're taking the limit is not something simple like 0 or infinity. Problems can still occur. Here we want to calculate the limit as x approaches pi over 4 of sine x minus cosine x divided by x minus pi over 4. Well, notice obviously as x approaches pi over 4, the denominator x minus pi over 4 goes to 0. What about the numerator? Well, remember, as far as the angle x is concerned here, thinking in angular terms, sine here is opposite over the hypotenuse, cosine is adjacent over the hypotenuse, and so when I take a 45-degree right triangle, which is what pi over 4 is in degrees, then in that case both sides are the same, and so sine pi over 4 equals cosine pi over 4. The two are the same. And so as x approaches pi over 4, I'm also getting 0 in the numerator. So now what we want to do then is apply L'Hopital's rule. That's the limit as x approaches pi over 4 of what I get by differentiating both the numerator and the denominator separately. Derivative of the numerator, derivative of sine is cosine. Derivative of cosine is negative sine, so we have negative sine, which is positive sine, all divided by 1. Now what happens? Well, cosine pi over 4, sine pi over 4 divided by 1 is a very simple finite number, so what we're getting, since they're both the same, is in effect 2 times the sine pi over 4 divided by 1. What is the sine of pi over 4? Let's draw ourselves a little triangle for reminder. Let's take both sides to be the same length because we have a 45 or angle of pi over 4 here. And so the hypotenuse has length square root of 2. And so consequently the sine of pi over 4 and the cosine of pi over 4 is simply 1 over square root 2. And so what we get then is 2 times 1 over square root 2, which is simply square root 2. Well, we can calculate limits using L'Hopital's rule even when both the numerator and the denominator are complicated. Let's look at one where we have trig functions in both the numerator and denominator. Here I want to take the limit as x approaches 0 of x times the quantity cosine x minus 1, all divided by the quantity sine x minus x. Now, in a sense, this thing is sort of doubly indeterminate. Notice that factor x is going to 0 as x goes to 0, but also cosine x minus 1 is going to 0 as x goes to 0. So consequently, we've sort of like got a second power of a 0 there. But look down in the denominator. X is going to 0, so that term goes to 0. And as x goes to 0, sine x goes to 0. Now I have the difference of two things, both of them going to 0, and so their difference obviously goes to 0. So this is sort of very indeterminate of the form 0 over 0. So sort of like 0 squared over 0 minus 0. But in any case, it's certainly indeterminate of the form 0 over 0. So let's apply L'Hopital's rule. We differentiate the numerator. Well, let's use the product rule. X has derivative 1 times the other factor cosine x minus 1 plus x times the derivative of the second factor. Well, that's negative sine x. And all this is to be divided by cosine x minus 1. Well, notice what's happening here. We've still got a problem. As x goes to 0, this becomes 1 minus 1, which is 0. And of course, as x goes to 0, that's very much going to 0. And down here in the denominator, we're going to 0. But let's simplify. We have the limit as x approaches 0. Let's break this up. In effect, the first term is simply 1, and we can cancel. So we just get a big 1 plus x times the quantity negative sine x, all divided by cosine of x minus 1. Okay, now we still have something over here to do, which is of the form 0 over 0. That's obviously in the numerator going to 0, and the denominator is still going to 0. So we can apply L'Hopital's rule again to this. On the other hand, the limit of 1 is 1. So what we have now is simply 1 plus the limit as x approaches 0 of x times the quantity negative sine x, all divided by cosine x minus 1. Okay, so now we want to deal with this last limit using L'Hopital's rule again. So here we have 1 plus limit as x approaches 0 of, now we differentiate the numerator again, and we have to use the product rule. Derivative of x is 1 times negative sine x plus x times the derivative of negative sine x, which is negative cosine x. And now we divide by the derivative of the denominator. That's negative sine x, and the derivative of 1 being 0. That's all we have. Notice the negative signs now cancel out everywhere. Plus, plus, plus. And so look, again, we can break this up as a sum of two terms. And in the first term, we have sine x over sine x, which is 1. So now we have 1 plus the limit as x approaches 0 of the quantity x cosine x, all divided by sine x. Okay, look again, we still have the form 0 over 0. So let's apply L'Hopital's rule to this limit. Differentiate the numerator and differentiate the denominator. So we have the limit as x approaches 0 of, well, the derivative of x is 1 times the second factor is cosine x plus x times the derivative of cosine x, well, that's negative sine x, and that's all divided by the derivative of sine x, which is simply cosine x. Well, notice now we no longer have an indeterminate form because down here in the denominator as x goes to 0, cosine x goes to cosine 0, which is simply 1. But I can break this up again. Here in the first term, cosine x over cosine x is 1, so I can say this is equal to 1 plus 1 plus 1 plus the limit as x approaches 0 of the last term, which is x times negative sine x divided by cosine x. Well, now this is not an indeterminate form. As x goes to 0, the denominator goes to 1, but look, the numerator certainly goes to 0, so this is just 0 over 1. So we have 1 plus 1 plus 1, which is 3, plus 0, so that's 3 plus 0, which is finally simply 3. Now, after a lot of work, a lot of applications of L'Hopital's rule, we finally get a very simple answer of 3 for this limit, and you probably would have never suspected that as the answer. Now let's use L'Hopital's rule to calculate the limit of an expression which arises sometimes in geometric summations. Here I want to compute the limit as r approaches 1 of the quantity a times the quantity r raised to the power n minus 1, all divided by r minus 1. Obviously, if I substitute r equals 1 in the numerator, 1 to the n minus 1 is simply 1 minus 1 or 0, and the denominator would become 1 minus 1, again 0. So this is an indeterminate form of the form 0 over 0. So L'Hopital's rule says differentiate the numerator and differentiate the denominator. Try again. So we want to look at the limit as r approaches 1 of what we get by differentiating the numerator and the denominator separately. Well, here we would have a times the derivative of what's in the parenthesis. Well, the derivative of r to the n with respect to r now is n times r to the n minus 1, and of course the derivative of 1 is 0. So that's all we'll get for the numerator. The derivative of the denominator with respect to r is simply 1. And so consequently what I get is simply a times n r to the n minus 1 evaluated at r equal 1. Well, if I put r equal 1, 1 to any power is still 1, so this becomes simply a times n. Well, we've worked some pretty tricky problems using L'Hopital's rule when the limits are of the form 0 over 0 or infinity over infinity. You might be led to believe that L'Hopital's rule is going to get you out of every tricky situation, but you would be misled if you thought that. Sometimes even L'Hopital's rule won't work and you have to go back to basics. Let's look at an example to see what can happen. Okay, here in this problem I want to compute the limit as x approaches pi over 2 from the left side of secant x divided by tangent of x. Well, as x gets close to pi over 2, tangent of x is going off to positive infinity as you come in from the left, and likewise secant of x is going off to positive infinity. And so this is an indeterminate form of the form infinity divided by infinity. And so we can apply L'Hopital's rule. We differentiate the numerator and the denominator separately now. Derivative of secant is secant times tangent. Derivative of tangent is secant squared. Well, notice what we're getting. We cancel secants here, and we end up with tangent of x divided by secant of x, and we're back to the exact same problem. Both the numerator and the denominator are still going to infinity, so let's try it again. Well, if I try it again, you can probably guess or realize I'm going to get back where I started from. Notice derivative of tangent is secant squared. Derivative of secant is secant times tangent. Cancel secants again. I'm left with the limit as x approaches pi over 2 from the left of secant x divided by tangent of x. And I'm exactly right back where I started from. L'Hopital's rule has not helped me at all. Well, what can we do with this thing? Limit as x approaches pi over 2 from the left of secant x over tangent of x. Well, let's look at it and keep in mind our trig identities. Secant of x is 1 over cosine of x. Tangent of x is sine over cosine of x. Well, now the cosine of x's cancel out. And so what I'm getting is simply the limit as x approaches pi over 2 from the left side of 1 over sine x. But, in fact, the limit as x approaches pi over 2 of sine x exists and equals 1, namely sine pi over 2. And so consequently, if the two-sided limit of sine x exists and is different from 0, then this left-hand limit exists and equals 1 over the two-sided limit, which is 1 over 1. And so that final answer is simply 1. In other words, here we have a situation of an indeterminate form, which was infinity over infinity. If we apply L'Hopital's rule blindly, we just end up going around in circles. But remembering the basics of our trig identities, we easily get the answer. Well, we've worked some problems calculating limits using L'Hopital's rule. Keep in mind that when applying L'Hopital's rule, it only applies to limits which are the indeterminate form 0 over 0 or infinity over infinity. Also keep in mind that to apply L'Hopital's rule, you are not using the quotient rule for differentiation. You're differentiating the numerator and the denominator separately. That is, you're saying the limit of f over g is the same limit of f prime divided by g prime. In fact, it's the only time you get to differentiate in some sense a quotient by differentiating the numerator and differentiating the denominator separately.